Sine and cosine. That's not what Wait, what? Yeah, so what if we didn't need to use sine and cosine? That's what Quaternions brings to the table. Another problem we have, I'm going to start off with this little video. It's kind of a cool way to see it. First of all, this is a homemade, this guy made this gyroscope in his shop at home. I mean, I'm just jealous. Let me see if I can get, how do I get audio out of here?
Did you end up buying that printer that you were just not trying to justify?
Yeah, it's in process. Let me see if I can tell it to go out. Without. Well, I guess so much for that HDMI interface. Wow.
The first one.
Is Interstellar theme playing at this moment?
Okay, well, I'm just going to turn it up here and you can listen on my laptop. All right. Can you guys hear this so far?
No, that was very quiet. Professor, is your volume down on the computer?
No.
Like when you're on the speaker setting, your volume.
This is volume right here.
No, but when you're on the first setting, like on the real time.
And then adjust the sliders for new chat.
He's trying to get him to
All right, so what we're talking about here is known as a gimbal lock. And when we use rotations, gimbal lock is a problem. You're asking, like, what the heck is gimbal lock, right?
Yes.
Some fancy sounding phrase. Gimbal lock shows up whenever you have things rotating about something else. In fact, a similar example is as you go from 0 to 360, what's the next number after 359?
360 or 0.
It's 360 or 0, isn't it? So 359, 360 or 0. What if you're only going between 0 and 359? And what happens to 359? What's your next number?
0.
0. Yeah. No, it's not. I'm only one away. So I can go plus 80 minus 180, right? When you do that, some things happen mathematically. It gets really tricky because your signs are going to flip on you all of a sudden, right? So it turns out physics knows this already. So we get this idea of gimbal lock. When we have co-aligned rotational frames, what we're going to find is this thing called gimbal lock. And this is what happens when we have those, basically that's what's going on. When we have this frame and this frame co-aligned, then what will happen is they're going to lock together and one's going to magically flip. You don't believe me? Watch the video. It shows it better than I can explain. So this is a gimbal. This is a gyroscope that he made. That inner thing is spinning. All of these are rotating about their own axis. So there's no translation, simply rotation. Sound fair? So we have a rotation about an x, a y, and a z. So each one of these can rotate independent of one another. Sound good?
Have two sets of gimbals. In a real system, we need three.
Right there, beside. That's gimbal lock. When they lined up and it automatically flipped, that's gimbal lock.
That's great.
Isn't it? Watch that again. I blinked and I just can't.
Have two sets of gimbals. In a real system, we need three. Each roll and yaw. But nonetheless, gimbal lock still remains a problem. Of course, just like everything else in life, it's not that simple. Watch what happens when the gimbal
Well-
rings live. This is called gimbal lock. And when this happens, for all intents and purposes, it's as though the gyroscope is acting on only one set of gimbals. And that, of course, is bad for calculating the guidance data. Now, I've only made this gyroscope to have 2 sets of gimbals. In a real system, we need 3, pitch, roll, and yaw.
Whoops, right there.
But nonetheless, the gimbal lock still remains a problem. Although it can be eliminated by some clever electronics and a 4th gimbal set. And just to show how counterintuitive gyroscopes are, watch what happens when I push the gyroscope. It moves at 90 degrees to the direction I'm pushing. Very strange. Well, I hope you found this video informative.
Anyway, I won't go through how he made it into his own little kill. I mean, he has a great little setup. Okay, but he actually handmade that thing. His hat's off. It's impressive. There are other things here that you can watch. Here's another one on gimbal locks here. You can Google this to your heart's content. There's another one I have in here too. Kind of talking about the idea of using the camera. So if you've ever done anything with Blender, 3D Studio Max,
In a real animation situation.
here this is kind of the same idea. When things are co-aligned. Whoops, let's just go back here.
In each case, gimbal lock occurs on the axis of the parent when the middle axis is rotated too far. Let's explore this in a real animation situation. Here's a 3D camera. We'll use the 3D software Maya. The bottom of the hierarchy is X, and in this example, it's pitch or tilt. As soon as the camera looks sideways, we achieve gimbal lock. This isn't good, especially considering that the camera will frequently look to the side. In this scenario, it's difficult to roll the camera because Z, our roll axis, has been aligned with X, our tilt axis. If we switch
So this is the Euler rotation matrices. Talk about it. It's the same matrix, right? These rotation matrices are all the same, the sines and the cosines. So the problems we have with rotation matrices is we can get gimbal lock. Whether it's from a mathematical perspective or from a physical perspective. That physical phenomenon is actually a result of the mathematical or vice versa. So it is dangerous. We can't tolerate that. Yeah.
So how do we approach that?
It's a great question. So what, right?
Yeah.
So we did this entire last month and a half, and I was talking about Euler angles and these rotation matrices. And now I'm coming to say, yeah, they suck. Am I right? That's what I just said. So what's the alternative? It's because we introduced them that way. Remember, we introduced this notion of rotation through the projection, where you have the sine and cosine scaling that as a function of that projection, right? But now I'm coming along and saying, yeah, that's bad stuff, because, in fact, it turns out, anybody know the history of, Artemis is launching any day now, isn't it?
Yes.
Right? So we're going back to the moon. Anybody know the story about the first time they landed on the moon? Has anybody watched All of Us? Or not, for All Mankind? It's a great show, you should watch it on Apple. I think it's on Apple. Go watch it. Your homework assignment over summer. Watch For All Mankind. The idea is, when they were landing on the moon, the Apollo mission was landing on the moon, they almost didn't land, they had gimbal lock. Because it lined up, went, oh crap. I think who was it, Buzz Aldrin who was the pilot?
Yes. Yes.
Okay. When he was flying, he even said he almost didn't land. He was down to like his last little bit of fuel. Gimbals were locked. He's piloting this thing manually because the guidance system couldn't do it. So you could stick a 4th axis on there, like you were mentioning, or we could look at this a little bit different. And that's where quaternions come in. All modern navigation, all modern robots don't use Eulers. As much as we've now talked about it, Coppellia Sim does not use Euler. Coppellia Sim uses quaternions. Quaternions are a way of describing rotations without the Euler angles or without the rotation matrices.
So this last month and a half has been a lie.
No, it's been an alternative reality. You can't understand the quaternions without going through what we've gone through, which is why we've done it. And for a lot of times, it's okay, but you will get gimbal lag. Navigation systems, submarines underwater, all Quaternions. I can guarantee that because I was on the team that designed the navigation systems for submarines. We went to Quaternions for a reason. Last thing we want to do is have the submarine get gimbal lock and not know where it's headed. That would be bad. You don't want to run to the side of the mountain underwater. Things that fly, all these UAVs, everything that's done on this weekend, crazy, right? All of the United States ordnance are using Quaternions for their navigation. I promise you that. No one's using it more than us because of things we just talked about. So what are these Quaternions, and how come I haven't heard of them until now? So Quaternions. A Quaternion, and by the way, you don't have to take notes unless you want to take notes. I published this under the 2D lecture, but there's no red boxes for you to fill anything in. Is that fair? Yeah. It'll go a little bit faster on this particular topic. But a Quaternion is a complex number that we're going to use to achieve rotation. It simplifies the mathematics. And so if we follow our mathematics this way, we will not get a mathematical lock. If we understand how everything is working, we can actually do this. Case in point, many of you guys know about BREX. Some of you may not know about BREX. BREX is Brockville Robotics Exploration. It's one of the research groups I started last year. Christian did the control systems for it last year. He had to move to Quaternions because he was getting gimbal locked mathematically. He goes, Dr. Boss, it's real. Yeah, it's real. It has to be used. Now I'm not just up here just doing this. It's real. It's a real problem. It's okay though, because like I said, that we've known about this for a long time, and we're going through the Quaternion math and show and why it's so much superior. It's a great read on if you want to look up on, I believe it was Hamilton, was it? Who invented it? It's a great read. Go check it out. History of Quaternions. But the guy was a bit of an ass who did come up with it. Just to tell you that. He didn't have a nice reputation. But it simplifies mathematics. We can treat a Quaternion as a rotation. And we can convert our Quaternions to a rotation matrix and vice versa. So when you guys had that example that you had to do that, or that homework assignment you had to do in Coppellia, all of that stuff was actually done in Quaternions. And then when you asked for that matrix, it gave you the matrix conversion. And we're going to look at that on Wednesday. So why Quaternions? And so you just got done seeing the idea of gimbal lock. When they line up, it locks. This is the gimbal spinning around. It doesn't really stop on gimbal. So on gimbal lock, it's just an animated GIF of time. But at any rate, Euler angles and matrices that represent the rotations that we've talked about, which can cause us mathematical instability that we will see, that you saw in that physical implementation, that we see when these two axes are co-aligned. So using Quaternions allows us to overcome this issue. I mean, last thing you want to do is have a robot that's got some co-aligned sensors, right? That's bad. So again, why Quaternions? So Apollo 11, when they were doing the moon landing, had a problem. One of the ways we could fix it was adding a fourth gimbal, and you heard it mention that on that video. Or you could also try to prevent the axes getting closely aligned within 90 degrees or any module thereof. But it can happen in anything: robotics, flight systems for navigations, etc. Also, if you're into animation, such as Blender or Maya, you can also have a gimbal lock, as you heard on that second video, which is crazy, right? So, does anybody actually use it? No. This is actually the notes from autonomous vehicles, why you see 4851, not 4751. So it's the same lecture, because it also works on autonomous vehicles, which Chris, by the way, did know about Quaternions. I don't know if he gave you guys that backup information.
No.
You guys are going to need those? Okay. So what is a Quaternion? The idea behind what a Quaternion is that it turns out we already know that an object can be translated using a transform matrix, right? And when we do that, the rotation matrix is defined by the identity matrix, right? All we're using is that p vector to represent the translation. Similarly, objects can be purely rotated without a translation when the p vector is 0. We went through all of that, it's just a little reminder. But downside of all of these, each one of these is a single rotation, right? We can only rotate about x, then y, then z. or z then y then x or something. We can't rotate them about, and this is why order matters in the Euler rotations, because we know that they don't commute. So the question is this, can we ignore this? Can we get out of this rotational sequence? Yes, by quaternions. So when you begin to hear all these positives about quaternions, you're like, man, this is really cool, right? This is easy. Now, if any of you knew Sam from last semester, he would say nothing's easy. Dr. Boston, it's not easy. Dr. Boston, it's not easy. The best impression I have of Sam, but it's probably pretty close. So, they are easy at the end of the day, yes.
So does this imply that order doesn't matter when it comes to quaternions?
Correct. Because you're going to see why. So what are quaternions? Quaternions are represented in the form of three imaginary values, I, j, and k. So the coefficients are a, b, c, and d. So the coefficient a, that's my real part. That's 1/3 imaginary, another third imaginary, the other third imaginary. Don't think of them as saying 1/3 plus 1/3 plus 1/3 equals 1, but it kind of does. So what happens is the I, j, k formulate the basis vectors, and that one, formulate the basis vectors or the elements of a space, a rotation space. Don't ask me where this guy came up with this and what he was drinking when he started, but it was rather than something good. So think of this as the real value, and these are my imaginary values, defined in three different quadrants. But here's the really cool thing. I can define each one of those as a rotation axis almost. So I almost want to think about it. So when we look at this I, j, and k, Remember, traditional I is imaginary in electrical engineering, J is imaginary, but now we have I, J, and K. So don't think about it as I or J, but I, J, K in quaternions all go together as a tuple. I, J, K is quaternions. Not I, it's not J or K, it's I, J, K. Quaternions, I, J, K. And then you have the real part. Everybody with me so far? All right, so it allows us, they're four-dimensional for all real numbers. Wait, what? Yes, I just said that right. They're four-dimensional algebra for all real numbers. You just said they're imaginary. Yes. We'll get to that. But they're used in all modern systems to describe pose on a flat or plane model. In other words, I can describe pose. We talked about what pose was. It has a position and an orientation. On the example that we did in Coppellia Sim, remember I called pose, right? Sim.getPose. It returned out four values. I said, four value is kind of weird. We're going to talk about it later. Well, now we're later. All right. Everybody with me so far? So, believe it or not, we can express a complex number to be a rotation. Man, if you just told me that before, instead of the stupid projection idea, you're right. You're going to look at this and go, oh, this is so much easier from the derivation. And I'll say, yeah, probably. But your book didn't use that, so I didn't want to confuse you guys first. All right, so we went through the book. We know we can describe this point in x and y as r cosine alpha and r sine beta. Yes? We've been doing this now since we were in kindergarten. And we know that my distance r is nothing more than the norm. Believe it or not, this is known as a norm. Which is also Euclidean norms, also known as Euclidean distance, but I'm going to teach you more math vernacular and call that a norm. But it's also the radius, right? It's all these things. And I know my angle alpha is nothing more than my arctangent of y over x. Nothing new here, right? Did I say anything nobody already know? So, suppose we want to rotate by some angle. Given that A is a complex number, that we're going to call A plus Bj. That's fair? And we know all the relationships from complex and the polar notation and the Cartesian notation of A. Everybody with me on this so far? I know in controls this is where some of you get lost. If you had instrumentation and controls, you might not have talked about the fact that a value could be, a complex value could be Cartesian representation simultaneous to the polar notation, but you remember that from your math class, right? And these were our little conversions that we had, right? All the same thing. But we want to rotate by some point from here to some point here. But we've already described that point through some angle alpha that we're going to rotate with the thing. Everybody with me so far on that? Yes, sir?
So is alpha from the x-axis to that y prime?
Kind of, sort of. You'll see in the next slide how it actually fits together. But yeah, that's because I wrote this as alpha. Because this is really my alpha, and I'm going to rotate by this additional value called theta.
Oh, gotcha.
I probably should have flipped them, to be honest with you, for clarity. Really. But what I really see is that final rotation is really by this theta plus this alpha, right? So I have this guy right here. So I have r cosine alpha plus theta and r sine alpha plus theta. Anything new here? So using my sine identities and my cosine identities, we get this. And all of a sudden you're like going, wait, Dr. Bosco, is that not yet? It is. X for rotation matrix. I know it's an easier derivation, isn't it?
Yes.
Compared to what was this rotation. I remember a couple of guys going, I still don't see the sine and the cosine. But I know you probably just accepted it and ran with it, yes?
Pretty much.
But now you're going, oh, damn. What's the question? Okay. A lot easier, but you can go, like, you just pull the coefficients, right? That's times this plus this. Done. So that was a 2D rotation about a complex. Can we do this with two more axes?
Two more?
Two more.
Yeah.
Yeah, it was so good.
If I do two more axes, I need two more imaginary numbers, don't I?
Yeah.
Like a j and a k, if it was dealing with an I. Yes.
Yes.
There's the magic of quaternions. The magic of quaternions is the fact that I can use that idea of this tuple. I have a tuple. It's a four-term tuple because I have my real, then I have my imaginary I, my imaginary j, and my imaginary k. In the same sense of imaginary values, where I had the Cartesian element, then I moved my Cartesian element, which was really a radius and a rotation, duality of a complex number. What if I had this not only about one axis, but I had it about three axes? Hence, my imaginary, my imaginary, my imaginary. Don't think of this as rotation about z, y, and x. Students have a tendency to do that. Don't. I still have a tendency to do that. I'm stupid. Now here's the thing. It's a complex value. A complex square is going to be -1. But in this case, it's the sum of the three squared is -1. Okay. And even more interesting is there's a couple identities. Think of this as my rotation. I times j gives me k in the plus sense. So this is giving me almost my direction of rotation. My j times my k is I. My k times my I is j. And if I'm going in the opposite direction, that's what that little minus sign is out front. So that j times k, I would say j times I is minus k. It's k, but I was going the opposite direction. Now, notice that I, j, and k are not commutative. I can't flip them around. J times I is not I times j, right? I times j is k. J times I is minus k, because I'm going the other direction. So they're not commutative. But notice the opposite direction, jk and kj, they're the same with that negative sign. Ki and ik. All right. This is something probably should have had maybe a couple of drinks first, maybe in the bar, I don't know. Like, cause like, well, this is like really weird. No, I'm just kidding. I don't condone drinking, and I don't drink. I'd rather have which I'm taking into account.
That's a root beer float kind of.
No, that's not true count. That's way too many. I don't drink soda anymore. Okay, so quaternions do a rotation. Did you see anything about a sine and a cosine?
No.
Is there any sine or cosine over here?
No.
So I times j is going to be a k. It's a rotation in one direction. A j times I is a minus k. No sine, no cosine.
No.
Remember, so calculating sines and cosines are expensive. So if we look at the addition, suppose we have two quaternions, ij, or p and q, and they're decomposed into their four element tuples. So q0, q1, q2, q3, p0, q1, q2, q3, and we're going to order ijk as 1, 2, 3 respectively. So we got p1i, p2j, p3k. They're not really unit vectors or unit axes like we talked about before. It's a quaternions. So when we do quaternions, they are a subspace vector though. So we see that subspace vector, what that means is elementally we add each one. So we have the reals get added together. The i's get added together. The p's or the j's get added together and the k's get added together. So in the multiplication, we carry out polynomial multiplication. So it's this plus this times this all the way through, right? Just like you did, remember FOIL, but they got four terms. So you get the four lines basically right here. Now here's the really cool thing. This turns into a negative because it's a square. Not all of them are though, because these are the squares, these are the non-squares. So I make my negative signs, I got a negative sign here, negative sign here, negative sign there, and then I collect all my i's, my j's, and my k's like I did from addition. And when I get done, I'm left with this, simplification. So this is just the value. Okay? I know it's got these four terms, 0, 1, 2, 3, 4. But it's kind of like when you look at it, it's like my diagonals in a way, if you think about it in a matrix. These are my off diagonal terms, or an I, J, and a K for each one. Everybody see that? It has like, how does each one contribute to each other? So if we think about it in the sense of a rotation matrix, and that scaling of the rotation matrix, we're kind of like scaling one with the other. Right? And it's contribution within each one into the I, for each one into the J, for each one into the K. Again, that's just a number. We have a bunch of little numbers to make that number, but it's just a number. Just a number, just another coefficient. So I have a B, a C, and a D at the end of the day. Everybody see that? That's multiplication for quaternions. Now we already talked about this idea of conjugates and absolute values. So in a complex value, a plus jb, its conjugate, use the asterisk to denote conjugate, is a minus jb. And we write that typically in the inverse. We talked about the inverse, remember? Of a vector is going to be the conjugate over the magnitude squared. So that's what we have right here. This is pretty straightforward. But if we look at that, this is again no different than what we had. So given some quaternion Q, Q1, 0, 1, 2, 3, where it's I, J, and K, 1, 2, and 3. Its conjugate would be Q, so again, Q0, Q0, and then negative, negative, negative for the I, J, K. Yeah.
Why is Q0 positive?
It's always positive. Because let's go back to what we talked about a conjugate. Is A positive? Yeah, both positive and both right. But the B is negative, right? But now we no longer have a single value imaginary. We have a three-value tuple.
Yeah.
Three-value tuple is my imaginary. So same thing happens. They just all attain that negative sign. Magnitude is also known as a norm. Becomes square root of Q0, Q1, Q2, Q3 summed together. Have I done anything that is like, oh my God, I don't understand it? No, right? Simple math, right? Even easier than what we've been doing before in some ways.
Yes.
But the concept is reaching. It's kind of out there, I'll be honest with you. So if I want to compute the conjugate and the inverse, I can multiply as Q star. And when I do that, I get my inverse. So that's how I compute my inverse of a value. So I can multiply these through, and my Q star becomes Q conjugate over Q magnitude squared. Okay. I'm not going to make you write all that out. We already did that multiplication before, except now we have negative signs.
What are our downsides when it comes to Quaternions?
We haven't been taught them yet. People find them confusing because quite often they're not taught. You guys are the first time I'm teaching it in robotics, but I did teach it for autonomous vehicles for the last several years. Not a lot of faculty teach Quaternions, at least in undergrad, and they should. They're not hard, but it's not typically taught. But what's funny is in practice, that's all we use. So I learned about them back in, not for my college years, but when I was working in Anaheim on the navigation systems for the submarines. And we all kind of learned, I remember Jeff goes, hey, we should use Quaternions. Quaternions. These are really, really cool. This is so easy. Why are we doing Quaternions in class? I don't know. Other faculty do teach them. I just haven't known of any faculty here that teach a lot of Quaternions. Maybe there are, and if there are, that's great. I think that's awesome. I think everybody should be teaching them, honestly, when we talk about robotics, autonomous systems, or any of that kind of stuff. So, how do we use a quaternion for rotation? Again, IJK is our real part. So, if we only deal with the pure quaternion, or the imaginary part, we're going to get a QR. So we're going to note Q is QR, where there's no, and this is kind of wonky. I apologize for the nomenclature. I'm following general principle styles. Because R could be like the real part. No, it's the rotation part. So don't think of R as real, R is rotation. I got rid of the real part.
Is the real part the rotation?
No, the real part is the magnitude. So think about that, this guy right here, in a way, it's not. Think of this as that P vector. It's not a vector though, it's a single coefficient. Because pose is defined as all four values. It could, think of it as R.
That's what I was going to say. So it's like arm length and then where?
Exactly. That's exactly. But in Cartesian, it's scaled by sine and cosine. And that's, we're carrying, think of this as the rotation about x, y, z with a magnitude radius. But it's not quite, but it's not the rotation about x, y, z as this coefficient is. So I don't want to mislead you. You can think of it kind of like that. It's similar, but it's not equal. Everybody with me so far, still?
Wait. So don't think of IJK as like a position.
Correct.
Because it's not a coordinate.
It is in quaternion space. That's what I said. So that's what I said. A, B, C, and D are values in their own space. The four-tuple quaternion space. Let me go back. So this all of a sudden, the math I showed you is all really easy, right?
Yeah.
But the concept is like, wait, what?
It's not as straightforward.
They form the basis vectors. 1 IJK. Not unit vectors IJK, but the basis vectors for quaternions.
Right, because IJK also has four variables.
It's a bad use of values, I agree. Yes.
So your IJK have space within their own realm, but the combination.
No, the combination of all four of these create the basis, which is the space. It's a four-dimensional space. And when we think of matrices, it's the basis vectors for quaternions, or quaternion space.
So we don't think of this as I in its own space. It's a combination of everything that creates it.
Right. Don't think of it as unit vectors. Think of it as quaternion. And this is where IJK gets. Yeah, a little bit of overuse. Yeah. overloaded with variables gets confusing. All right, so where were we?
So what defines your rotation is that quaternion.
The quaternion IJK, just like, again, IJK is an imaginary value, yes? And we showed very simply how a very simple two-dimension about rotation about one axis can be performed. Remember, that's what we said right here. And we said that this is for very simple complex values. Right? This was our complex, right? These are our complex relationships. My Cartesian and my polar representation. And you all nodded your heads, remember? And I said, what if we did 3 of these? So I have to have 3 complex values. And you all nodded your heads. You remember doing that?
Well, because that makes sense. Then how do you put them together?
Oh, we'll get to that one.
Okay.
That's coming up. Okay. So we did some preliminaries, right? So here we are, quaternions for rotation. Okay, let's go back to this one. I'm going to ignore the radius magnitude component. I'm simply dealing with the rotational component. So when we want to rotate, or when a rotation is going to be performed by a quaternion R, that rotation right there is defined by these 3 values. My quaternion defines my rotation. Everybody get that one now? You know, if you don't believe me, we go back to that 2D case. But in the 3D case, we have to carry the other 2 variables, or the other 2 subspaces. Everybody with me on that? So if I multiply by a quaternion, I perform a rotation.
That makes sense. Yes.
Anywhere in this quaternion, do you see a sine or a cosine? They're evil. Do you even see a matrix?
No.
What's a matrix? Boy, you forget easily, Jessica. Like a goldfish. No, I'm kidding. 3 seconds done. Okay, so a rotation is going to be performed through this quaternion QR. We're going to call it QR. So it's similar to the rotation, similar, not equivalent, of the unit vectors, where the norm of QR is equal to 1. It's not the same. I don't want you to confuse that. That's why I said similar, but in your mind, I do not want you to equate the IJK of a unit vector to be that of the quaternion IJK. Everybody with me on that? In fact, I've been saying IJK as if it were one word on purpose. Not unit vectors IJ and K, the quaternion IJK. I know it's stupid English, but it's the best way I can come up with it. So use the fact we overloaded the IJ and K.
I want to clarify. So your quaternion is made up of 2 things, 2 components. Your real value,
Yes?
and then your quaternion,
What quaternion imaginary value?
which is your IJK.
IJK.
Okay.
Yes.
Thank you.
It's the best way I can differentiate for you guys. So, if I want to rotate A and B are represented by quaternions, then the following operation can perform. We're going to pre-multiply A by QR, and we're going to post-multiply, this is the process, A by QR, conjugate. This is the process. So, if you're Mandalorian, this is the way. Actually, no. What was the character who wasn't the Mandalorian? It was the other version. What was it? Who was the one who said this is the way? Or is that Mandalorian? Oh. Anyway, so this is the way. So it's QR. So it's rotations. So this is the way. Yes, this is the way. So it's rotation, amount times rotation. Conjugate. Okay. Because there's no real component in the quaternion, then QB will be a pure quaternion in that sense. So, using quaternions, I'm going to rotate through a quaternion. Again, Q0 should be 0. But QA may not be, but it doesn't matter. So we're going to multiply through, Again, this is just, however you want to work the multiplications out, doesn't matter, but this is a triple polynomial multiplication. Yeah, it's tedious, but it is what it is. At the end of the day, though, we can do this construction in a matrix, believe it or not, which is always nice. But, and here's the but, when I said real numbers, what I meant is although we're multiplying representations of complex values, I'm just multiplying a value times a value times a value. And so that's not a complex value anymore. Yes, this is the composition of a complex representation. I agree. But when I do that multiplication, it's just a number and a number and a number and a number. You all see that? So that's what I meant when I say they're just real numbers. They're just numbers. Who cares if it, yeah, I know in summation or in combination, that's a quaternion. And that's a real. We said that. But when I'm doing the arithmetic, I got a number times a number. And I'm grouping it. I got a number times a number and I'm grouping it. That's it. Keep track of which variable is being multiplied, which variable, and call it a day. No cosine. No sine. No decomposing a complex number into its real component and imaginary component. It's already like that by definition. It's just a number times a number. That means calculating them is very, very fast. Very efficient. We don't have to worry about all these complexities of inversions of a matrix, which we talked about. Now I can represent the quaternion as a matrix, and that's what we see right here. And so this happens to be the value, so I can pre-compute my quaternion as a matrix representation. So this is the diagonal. What's kind of cool is when you look at the diagonal, you just have to see where is the plus distributed on the quaternion values.
It goes like.
Exactly. Kind of cool looking, isn't it? And it kind of makes sense, right? This is the one about the kind of. Okay, this is not a one-to-one. But this kind of rotation about x, rotation about y, rotation about z. If we think about that. But it's not. It's a quaternion k.
Question?
Yeah.
Where's the oh, okay, never mind, you're multiplying them together. I was gonna say, isn't it four-dimensional, but no?
No, it's three. So what we do is we should the I, j, and k in the x, y, and z's.
So for that one, we don't use that at the bottom, the 0, 0, 1.
Nope.
No.
Nope. This is a quaternion. That's a rotation.
Okay.
That's a rotation matrix.
Would you treat your quaternion as a matrix, or is this?
Yeah, you can do it. You can definitely do that. And so here's the identities. So your magnitude is nothing more than this. And again, if we go back, we can derive this. I'm not going to go through and waste your time on that, but we can derive the relationships of the quaternions of this guy equal to these guys. So we're just using the identities. You can plug and chug and get them out. That's fine. Which is kind of cool. Right? So these two equal these three. These two equal these three. These two equal these three. Because this is a distance. Remember, that's norm. And the norm. And remember what happens if you multiply two of them together and get the third one. 5j times. You think about that. This is kind of thing. No, I'm not thinking about that. I don't want to upset them. Okay, so quaternions as a matrix. I could look at something that looks like this. Right? So representing an operation, quaternion B is rotated through a quaternion QR from A. And I could pull values out if I wanted to. So I could, I don't know if you noticed, there's no here. I could take that 2 out and simplify that matrix here. But when I do that, clearly I have to get a 0.5 in there. So that's just a simplification. A couple of other things on there. Given the rotation matrix M, so this is what you know. How do we get to the quaternions? So this is how you get to the quaternion Q0, Q1, Q2, Q3, given the matrix. So given that 4x4 matrix, or the rotation matrix is a 3x3, so I can ignore the position, just dealing with rotation. So I'm going to take that p vector and that bottom vector out. I'm just dealing with the rotation component to it now. I take the trace of that matrix, which is the diagonal, and I sum them up. When I do that, this is what my matrix was. That's what we had from before. So I'm just taking that and I'm summing them up, and I'm getting to get 4 Q naught minus 1. So we find that we can now solve for Q naught becomes the trace of our M matrix plus 1 over 4. So if you want to kind of go back and forth, how do I get my Q0 term from a rotation matrix? When in Coppellia Sim you asked for that rotation matrix, it did this because it was living in Quaternion land. It doesn't use Euler. It doesn't use rotation matrices. It uses Quaternion. Well, what's my rotation matrix? Oh, dummy again. Okay, here you go. Here's your rotation matrix. When are you going to come up to the rest of the world? Okay, join the rest of the smart people. Yeah.
Is there a reason the book doesn't go over Quaternions?
You didn't have to ask the author. I don't know.
Let me just send an email real quick.
I think it would be a good addition, to be honest with you, because you can see how easy they are. Again, Coppellia Sim uses Quaternions. I didn't teach Quaternions in last year's robotics. I was talking to some students and said, you should just throw in Quaternions. They were in their autonomous vehicles class, and they had me went over Quaternions. Fine, just using the slide numbering from there. But they said, you should have this in robotics. Okay, we'll throw it in. It's a 1-day lecture. I will give you a homework assignment. Yes,
Do
sir.
we get to choose which way we can use the exam?
What do you do? What?
In the exam.
Like in the exam?
Oh, no, I don't care. Honestly, it'll probably be, I don't know. I'll probably give you a standalone question for Quaternion by itself. And then the other one probably be better because you develop your, to kind of go back, your transform, when we talk about some of the other characteristics of what transforms do, we'll find why we use a transform as opposed to a Quaternion. So, you're probably going to still stay with the transforms and rotations. But when we go to the Jacobians, which is the next chapter, we'll see the use of the transforms, which are composed of R and P. So that's why we do talk about it, and they're so useful. Could you do that in Quaternion space? You can, but it's not as intuitive to do that. Yeah.
That means the Quaternions are mainly primarily used for rotation.
Correct. And represented rotations.
So you would have transforms for translation.
No. Okay. But when we go through what are called Jacobians and differential velocities, yes, we'll use transforms. But the transform can be represented in a Quaternion in a A or Q naught. So this is how we find Q naught. Similarly, again, going back to this matrix right here, we can literally just take this guy and equate them to one another, which is all it's done here, and say, okay, M11 is this, so Q1 kind of combines. So we already found Q0. Now we need to find Q1, so we can find Q1 in terms of M11 and basically Q0. So that's all we're doing here. And interestingly enough, Q2 is M22 plus Q naught, and then Q3 is M33 over 2 plus Q naught. Which, again, kind of makes sense, right? When we think about it, it's not a one-to-one though. That's why I'm trying to say these aren't one-to-ones. The J, the unit vector J is not J in the Quaternion element. I is not I in the Quaternion element. J or K unit vector is not K in the Quaternion element. They are different. All right. So when we have an Euler angle to convert to Quaternion conversion, so given the rotation of an angle, there's a corresponding Quaternion is found. So again, this is some matrix, right? So we're going to rotate about the z-axis. What's my Quaternion? And notice, have I said anywhere that there is a Quaternion for rotation about x, Quaternion for rotation about y, and Quaternion for rotation about z? No, it doesn't matter. Doesn't matter. This is a rotation about z. And I can find a Quaternion for that by just going through the equations that we got right there from before. So we find the trace, find Q naught, and this is what we're going to do. Find Q1, turns out to be equal to Q2, which is going to be 0, and Q3 is going to be sine over 2. Now what's interesting is this is what we're going to get. We're going to get K sine over 2 plus the cosine. So think of this as kind of like rotated about the z, so we see the K showing up, where the other two were zeros. which kind of makes sense. Again, there's a similarity between them. There's not an equality. It's not, that's why we have this right here. This is the equality. So this is rotation about the side. That is going to be this guy right here. That's how we find it. The only reason we have sine and cosine is because we're making the conversion between the two spaces. But it's the same point. That point here can be represented through a quaternion, or it can be represented through a roll, a pitch, and a yaw, and a translate. Everybody get me on that one? Which is how we compose the universal rotation matrix, right? It was a rotate about XYZ times the translate. So we do the next one right here, which are the same ideas. So we're going to rotate about phi and rotate about theta. And when we do that, we're going to each one of these, we see kind of that cosine phi, basically that cosine angle over 2 plus the I, the j, and the k. It's rotate about z, rotate about x, rotate about y. Again, I didn't show the decomposition for each one of those, but it's the same process. We can look at it. So what does that mean right here? So this is kind of a summary of what we did. And so if we want to do a rotation of 90 degrees about the z-axis with a p vector that's located at 1, 0, 0, this is what we're going to have, right? That's the expression of the quaternion. So if we want to convert that matrix to some quaternion, this is the matrix that we have right here. So this is my rotation matrix, 90 degrees about z. This becomes my quaternions. These are equivalents. So I just put the values in here, solve for Q0, Q1, Q2, and Q3. And this is what I'm going to get. Radical 2 over 2, 0 and 0. And then Q3 is radical 2 over 2. And then my QO and my QR conjugate is just changing my signs. So my Q naught, I find my real component, then I find my K quaternion component.
Professor,
Yeah.
where is trace M? Like, what's
My what?
the trace M?
Trace, that's just the trace going back from here. This is just the definition.
Oh.
It turns out when we go through and do all of these things together, we'll find to solve for Q naught, we're going to get to the trace of M11, Q2, and Q3.
What does trace represent?
It's the sum of the diagonals.
Oh.
It's known as the trace. Which, by the way, we did talk about briefly on that primer. I don't know if you might have missed the primer.
So you're gonna sum all this?
Just the diagonal.
Oh, okay, all right.
Right.
So when we're converting from U to quaternion, are we always only resulting in one imaginary part?
Only if we deal with one rotation. But I'm going to do subsequent rotations to then compose each one of those. Right, so here we have the other one. So we do the I and the J as well. So we compute the real and the I and the J. So putting these together, the quaternion of B becomes QR times QA times QR conjugate, which is what we're doing right here. So we're going to get the I's and the IK's. That's going to make that into a J, right? We're going to go through this and get these values, and then this becomes a minus I. That cancels out with this. This becomes a J, and we're simply going to get the answer as J. So the answer is exactly what we'd expect, right? We rotated about 1 by 90 degrees. Now we're going to have the value of J. That's exactly what we get. I'm right. Now we get the rotation about J. That's the same as doing this guy right here. I have a homework assignment I'm going to give you guys to work on for quaternions. I'll post it for you guys tomorrow. tonight.
Professor, can you extend the previous homework, please? Can you give us the Wednesday instead today?
You guys want today, tomorrow, on Wednesday?
Instead today, Wednesday for the second homework?
Oh, for the,
For the robot arms?
sure, I gave you Wednesday.
Oh, no, you said second,
The second,
March 2nd.
I know, I can give it to you.
Oh, okay, okay, all right. Thank you.
Here you go. So you want to extend the due date? Sure.
Yes, thank you.
We'll just do it right now. How's that sound?
Yes, that sounds good.
Okay. So this one right here?
Yes.
All right, so let's do this. So let's edit it. Hang on. I'll give you more time.
Oh, thank you.
Some of you have submitted it, FYI, but I will, if you want to resubmit, I'll do that. Does that sound good?
Yes.
Yeah.
Professor, is there a prompt written anywhere for what we're supposed to be doing in Coppellia for our homework?
Not yet, right? You haven't
I'm
posted.
gonna give you that one.
No, not
I'm
yet.
gonna give you that
He
one.
will give it to us.
Okay.
Which one are you talking about?
Anything involving a simulation or?
Oh, no, I haven't given you, I've not given you a simulation yet.
So all that's due is.
I gave you the one simulation, the one I actually asked you to do, we rotated the cube. Didn't I
The
give you that
cube?
one?
No.
No, I haven't, there's been no prompt of that.
Yeah.
Oh, that's right, I held off.
Okay,
You can do that part still.
Okay.
I just showed you guys how to do it.
Yes,
I posted
yes.
that notice by recall. Yes.
So, but you haven't,
I saw you posted the videos today.
Okay,
but you haven't assigned it, right?
I have not assigned the simulation, no. No, that's coming up.
Okay, all right.
Yeah, so we're gonna do a simulation, it's gonna have a couple different things to it, some components to it. It's gonna have, some Coppellia, in fact, I'm gonna probably do is actually not put the quaternions in the simulation, that's gonna be a separate assignment.
Okay.
Okay. No, the reason why I was holding off is I wanted to get the homework out of the way before I gave you the simulation assignment.
Okay.
Because they do go hand in hand.
Okay.
Okay, so, question?
Does it matter if we use ij equals k or ij equals negative k?
No, it doesn't, it does matter. Ij equals k, ji equals minus k.
Okay.
So that's the direction of rotation.
Yeah.
That you have to adhere to, you have to do that. Okay. So I'm gonna give you a homework assignment on quaternions, it'll be separate from the simulation. Okay? Okay? The reason why I want to give you the simulation is I want to make sure you felt comfortable doing the homework, which is due today. So I was gonna give you the simulation on Wednesday, I'll do the simulation I'll post it on Monday.
Okay.
I think I'll give you guys a quiz this week on this topic now that we've gone over. A different kind of quiz. This will be like just a campus quiz.
Okay.
On quaternions?
Huh?
On quaternions?
No, on rotations.
You said two.
Rotations or like of the frames?
Yes, on DH parameters.
DH parameters, okay.
It'll be a simple quiz that you can practice.
Okay.
So what you have to, so let me make sure you guys are all clear. So I'm gonna make this, change this to date. Is that good?
Yes.
This is the homework assignment that had the 10 questions or the PowerPoint slides or whatever I gave you guys, right?
Yes.
Now, let's change the other one as well. How's that sound? The quiz issue.
Oh, the, yeah.
That one
The
is.
quiz work.
Yeah, you can change that one.
The quiz work. So it's the combination of a quiz and homework. I've never called it quiz work before. Literally, that came out of my head today. So no, it's not something I've ever used. But let's set it down. Okay, so that's the stuff. That's the one you guys started working on last week as a group.
Yes.
Yes, yes.
Yes.
So we are going to move that date.
But that's gonna be individual, right? Everybody's gonna submit it.
Yes.
Okay. All right.
But,
It's for 0 points. It's for 10 points.
I think we should.
Question?
We have presentation on Wednesday.
Yes, you do, but that's in lab.
Shouldn't that be like a part of the?
That's why it's due Wednesday.
Okay. That makes sense.
I was having, the reason why I had you before was just so that you guys felt comfortable doing it. But I'll let you guys have till Wednesday. Okay. I want you to make sure you know what you're doing. That's really what it boils down to. Sound fair? And if you build the arm in Coppellia, that I gave you those videos, and all of the videos from robotics, you can walk yourselves through that. And literally build your arm. And if you use the Coppellia notation on how you go from one joint to the next, so this is the Coppellia /Craig notation, I'm okay with that. only worth 10 points. It's practice. Simulations are worth more than practice points. They are worth more, as I've said all along. 3 simulations, I think, is 1 grade, or exam grade. I want to make sure you guys know what you're doing before we do the simulation. That's why we're doing it. So I don't want to push back more than that, so that just means on Monday I'll assign the simulation, as long as everyone's comfortable by Wednesday to do this. Or at least feel comfortable enough to go into doing it. You especially even using Coppellia. My suggestion to use Coppellia, remember I showed you guys how to do gauge parameter extractors from like the other arms on there?
Oh, yeah.
Use the other arms. You know your X, Y, Z because you see it. Practice, see if you got the right answer. It tells you right there. You all make sense? Is that going to show you what I'm talking about again? You want to see Coppellia real quick?
Yes.
Yes, no, because we're done with
Yes,
Quaternions.
yes.
Okay. So we have, let's edit this. It's due date. Already did. Okay, just didn't show up right there. Refresh it. All right, 4-4. Good. Okay. So we're going to go through Coppellia here. So I was going to show this to you guys on Wednesday. And on Wednesday, we'll go through that, and we're also going to do inverse kinematics. Let's go ahead and pull. I'm going to pull up rotate Q. And I'm also going to add in.
Professor, with this Coppellia, can we build this?
Yes.
Yeah?
Yes.
Oh, okay.
If you want to. I would. That's a pretty big. Actually, it's already in there.
Is it already?
I'll give you the model.
Oh.
How's that sound?
Yes, that
All
would be
right.
good.
So that's this one right here. Oh, no, it's not.
No, that's not it.
Never mind. I take that back. I don't have it.
You don't have. Oh.
No, I don't have it. You can build it, yes. It's got the prismatic joints, so it's a little tricky. That's what I haven't done. Okay, so again, where's my XYZ? Now, these are I think I said I was going to give you guys extra credit if you brought one of these in. So what I want you guys to do is, where you see them? So take a picture real quick with your phone of your beautiful widgets and email me that picture. It's dated and it's timestamped on that picture, so I know you're doing it right now. See how that works?
Maria, can I temporarily hold that one?
You're not even in the class. Do me a favor on the subject. Put down manipulative. No, that's too much typing. Put down XYZ. Sounds good. Put down XYZ
Planes.
on the subject matter and your last name.
Okay.
Take a picture XYZ space last name. That's extra credit, remember. Okay. So I'm going to use Maria's because it's nice and big. I like that. You guys can all see it. And so if you notice, that's what we have right here. Right? That's what we have. Oh, you have part of the other one here.
Yes.
I'm just going to have to make some of these. All right, so XYZ is looking like this. Right? No, there we go. So what do you have as your X? Did you?
It's the red one.
Okay. Okay, so I'm going to do it like Coppellia. It's got the color. So Z is pointing up.
Uh-huh.
Sound good? Yeah, you're going to have to change your blocks. I would just put tape around it.
No, yeah, I would put the letters, yeah.
And then put a letter on it. Yeah. All right. So here's XYZ. Now, notice, let's go ahead and open this up. And that's why I want you to make 2 of these, at least. So you can open this up. Go to UR3. We're going to click that end link down here. Go down to Tools, Modules, Kinematics. Go to Dedeman-Hartenberg Extractor, and there it is. The other thing I want you to do is you can click on this guy, and you can see where its X, Y's, and Z's are. So you notice the X that we have right here, the Z is pointing up. But now, we went ahead and rotated to get to that next Z that we have right here. It's going in this direction, right? And so here's the X, and we rotated it by 90 degrees. So that's what we see here. But notice to go from this guy right here, we actually rotated about Y, right? So to get that one here, how do we do that? We rotated our theta with a 180. Who keeps eating on dang? So, it's all you guys. I forgot about that. Never mind. So, use your manipulatives and use the X, Y, Z's that are in here with the table that gets generated for you. And you're going to see when you have these alphas, and when they not have these alphas, and it's plus or minus 90. So practice with it. Coppellia gives it to you. There you go. So y'all have arts and crafts in this week. What it really boils down to is how you start this. If this was rotated, I mean, I'm rotating because I'm rotating me. But again, these are all rotating together. If I rotated this guy here, relative to parent frame, so I'm going to move this guy here. I'm going to see that show up down here.
Did you rotate it again?
Okay, that's not going to show up. Yeah, I have to redo the where is it at? And that's in here somewhere.
I thought it did update to your manual updation.
Yeah, actually it didn't. So it should. I'm not sure why it didn't do that.
I think you've done this.
But I think this is the comment that's written in there is there's an infinite number of definitions. So it depends on how you set the directions of the XY axis around there. That's the key thing. So actually, this one doesn't fit. It's using its own universal frame. Okay, quaternions. We'll do some examples of quaternions through the scripting that I showed you right here. I'm going to give you some homework to do quaternions. We'll do that on Wednesday. And we're also going to do inverse. I'm going to start inverse kinematics in Coppellia Sim. Yay! On Wednesday. On Wednesday, we'll be meeting at 8 o'clock. You are doing presentations. You are doing the mechanical detailed design. My recommendation, bring your mechanical design.